So, questions about last class? And then for those who are watching, so there are no subtitles, so you can use the YouTube subtitles, but we won't generate them. And also, those who are watching will not, there will be no exams or no lists. So they will get just a grade which is O for Ovinch. Okay, so let me continue what we were doing. So we defined this discrete times Markov chain. And we proved that the very important property about this Markov chain is that if you condition your chain that at some time k it is at some site x, then this probability defines a new Markov chain. So if you look at your chain starting from this time, so you say that you compute the probability, let's say that at x plus 1, there is some echo, no? Tem eco. Vocês conseguem melhorar? So xk plus 1, it's equal to xk plus 1. Xk plus n, it's equal to maybe x1 and xn, given that xk is equal to x. Then this corresponds exactly to start at time 0 from site x and consider a new Markov chain which starts at 0 at this point, so that this is equal to x1 equal to x1 up to xn equal to xn. So if you know that at some time k you are at x, what happens in the future, it's exactly what happens to the chain if you start at time 0 at x. Okay? So, and we use this property in our example, and maybe I want to come back to this example. So we had here a Markov chain which jumps with probability p to the right and q, which is 1 minus p to the left, and say that at 0 it remains at 0, and at n it remains at n. Then I defined tau as the heating time of the set 0 and n. So tau is the infimum of n larger than 0, such that xn belongs either to 0 or to n. Let me call the set 0n as b. And I wanted to use this property to show that starting from any point x, tau is finite with probability 1. Okay? So this is the central property. So I want to rewrite again the proof that this probability is 1, just to make sure that you understand how to use the Markov property. So what I said, in order to prove that this probability is 1, it's to try to find a relation for fx. So you define f as this probability, and you want to find an equation for f. So just recall that px, it's given as the probability condition that at time 0 you are at x. Okay? So what we did, we computed this probability according to the possible jumps at 1, and then we decomposed. So we wrote fx as pxy, y in E, and then the probability that tau is finite given that x1 is equal to y. So I won't come back to this identity because this one is simple, and I'm here assuming that x is different from 0 to n. And what I want to show is that this is equal to the probability that you start at y, that your time is finite. Okay? So I want to reprove this identity in order to make sure that you understand. So, and what I want to do is to use this property here. Okay, so what I'm saying is, let's write what is t less than infinity. So I want to write this set as the union. Mind that since x is different from 0 and n, so on this probability, under this probability, this event, tau cannot be equal to 0. Okay? So tau is larger or equal than 1. And so I will write this as tau equal to k. Okay? And tau is equal to 0. It's empty because, well, I'm starting from x, and x is neither 0 or n. And so what is this? Okay, so let's use this to say that this probability that tau is less than infinity, given that x1 is equal to y. So it's equal to this union, and since these sets are disjoint, this is equal to the sum. All right? So now what is tau equal? So tau equal to k. So the first time you visit the set B, it's at time k. So this is exactly equal to, well, the fact that at x1 you do not belong to B. So remember B is 0, 1, n. Then x2 does not belong to B. Intersection x k minus 1 does not belong to B. Intersection xk belongs to B. Okay, so this is obvious. And so I can write now that this is x1 does not belong to B. Xk minus 1 does not belong to B. Xk belongs to B, given that x1 is equal to y. Right? And now I have an expression which is exactly like this one. Okay? Well, the only difference is that I have also xk here, but, well, I can also put xk here. Okay? The same, I could have xk equal to x0 in this equation. But just mind that since xk is equal to x, this will be either 0 or 1 if xk is x or not. So if now I write, well, x1 does not belong to B means that x1 is equal to from 1 to n minus 1. The same thing here, so I can decompose this probability as a sum of probabilities, and there I'm exactly like that. And so I'll just now apply what's written over there. And what's written over there is that since I know that at time 1 I'm at y, it's like starting at time 1 a new Markov chain, which starts at y. And then everything it's translated back to 0. So time 1, it's now time 0, time 2. So this becomes x0 does not belong to B. x1 does not belong to B, up to xk minus 2 does not belong to B, xk minus 1 belongs to B. Okay? Mind that I'm translating back, because the chain, it's starting anew at time 1, here at time k. And this is equal to the probability that, well, I'm not at B at time 0, I'm not at B at time k minus 1, but I'm at B at time k minus 1. So this is tau equal to k minus 1. And now the probability is starting from y. The chain is starting from y. So what we proved is that this sum, it's equal to the sum for k. Remember, k is larger or equal than 1. That the probability starting from y, that tau it's equal to k minus 1. Which is the same thing as taking j larger than 0 and tau it's equal to j. Because now starting from y, maybe tau takes the value 0, because y can be equal to n. Okay? So under py, the event tau, it's finite, it's equal to a union which now starts at 0. Because maybe y it's equal to n or y it's equal to 0. Okay? And therefore, once I have this, I can write that this is exactly the probability starting from y that tau is finite. Okay? So if you want to really apply exactly what's written, what we proved, here is the way in which you argue. Okay? But of course, we won't write all these lines. We will just go from here to here, saying that, well, you're using the Markov property. Questions about that? This is very important. Essa igualdade? Então, é exatamente essa igualdade em que eu estou aplicando o que está escrito aqui. Tá? Aqui no meu exemplo, k igual a 1, esse x é o y, e eu estou simplesmente escrevendo, passando daqui para cá, utilizando. Tá? Então, a única, em todas essas contas é álgebra, aqui eu estou usando a propriedade de Markov. Tudo bem? Okay, so I wanted to give all details to make sure that you understand. So this is the first remark. Okay. Then I want to prove a second lemma. And this second or third lemma tells me that this is a property I mentioned before. It's that given the present, the past and the future are conditionally independent. So what I want to, the formula I want to prove is this. I fix a time k. So I will condition the past and the future. So I take x0, it's equal to x0, up to xk, let's say it's equal to xk, xk plus 1, xk plus n, given that xk is equal to x. So here again, I can forget about, I can include it, this event or not, because given that xk is equal to x, this is either 0 or 1, okay? So I can always erase, but let's leave it in this. And what I want to say is that this probability, it's equal to the probability that x0, so the past, say including the present, given that xk is equal to x, times the probability that xk plus 1 it's equal to xk plus 1, xk plus n, it's equal to xk plus n, given that xk is equal to x. Okay? So this is telling me that if I take an intersection of an event from the past with an event from the future and a condition in the present, these probabilities are equal to the probability of the intersection. It's equal to the product of the probabilities, and therefore, what I'm saying is that these probability, it's actually, well, these events are actually independent. Okay? And mind that by the Markov property, this event, it's equal. So I'm conditioning that I'm time k, I am at x. So this is starting from x. x1 is equal to x1. xn is equal to xn. Okay? This is by the Markov property. So let's prove this lemma. And the proof, it's easy. It's always the same. Well, let's write this conditional probability as the probability of the intersection over the probability that xk is equal to x. So this is the probability that x0 is equal to x0 up to xk equal to x, xk plus n equal to xk plus n, divided by the probability that xk is equal to x. Okay, now let's use the formula we proved for this probability, right? We know that this is mu x0 p x0 x1 p x k minus 1 x p x xk plus 1 p xk plus n minus 1 xk plus n, and this is still divided by the probability that xk is equal to x. Okay, so now if I look at this probability, this is exactly the probability that starting from x, that x1 it's equal to xk plus 1, xn it's equal to xk plus n. Okay, so this product, if you remember this formula, which we used already here, this probability is exactly equal to this product, and this is what I wrote here, which is equal to that. Okay, so we have already obtained this first piece. And now let's look at this piece. Well, this piece, it's also equal to the probability. Remember, mu, it's the initial distribution of x. It's the distribution of x0 under p. So this is the probability that x0 is equal to x0 until xk equal to x, okay, k minus 1, xk equal to x. Then this is multiplied by this probability. And it's divided by the probability that xk is equal to x. And now if you look at this expression divided by this one, this is just the probability of this event condition that xk is equal to x. Okay, and so this is the first piece. And we already obtained the second piece. And mind that here, if xk is different from x, everything is 0. The left-hand side and the right-hand side are 0. So I can admit that xk is equal to x. And this is exactly what we get when xk is equal to x. All right? Questions? So if you're watching and you have questions, you can ask your questions in the classroom, in Google Classroom. But actually, what we'll prove is that these are, so what we proved is that if we have a Markov chain, then the past and the future are conditionally independent given the present. Well, actually, the converse, it's also true. So if we have this identity for all k and all sequences, then we can prove that the Markov property holds. So what I have to show, so is it clear what I want to prove? I want to prove that if this identity holds, then the process xn, it's a Markov chain. Question? I thought someone said something. Okay, so in order to show that xn is a Markov chain, what we have to prove is that the probability that xn plus 1 equal to xn plus 1 given that x0 is equal to x0, xn is equal to xn, that this is p xn plus 1. So let me write this probability as the probability that xn plus 1 is equal to xn plus 1 up to x0, it's equal to x0 divided by the probability that x0 is equal to x0, xn it's equal to xn. And now I will condition in the numerator I will write the numerator as the probability of what's written there, given that xn is equal to x, xn times the probability that xn is equal to xn. And this is divided by the denominator. Then let's use this property. So this is telling me that this is equal to the probability that xn plus 1 is equal to xn plus 1, given that xn is equal to xn, times the probability that x0 is equal to x0, xn is equal to xn, given that xn is equal to xn, times the probability that xn is equal to xn. Okay, so I'm just now here I condition on the present at time n, and now I use this formula, which is telling me that given the present, what happens after, which is xn plus 1, it's independent of what happens till xn. So this is where I'm using the hypothesis, and this is still divided by the denominator. Okay, and now, well, this conditional probability times this probability is equal to the probability, so this is equal to the probability that xn plus 1 it's equal to xn plus 1, given that xn is equal to xn. And this probability is exactly what appears in the denominator. Okay? So once you multiply this conditional probability by this probability, you get the probability of this event, and this is exactly what's appearing in the denominator. So this is equal to what? And this is what I wanted to prove. So I didn't prove what I promised, because it's wrong. What we proved is that it's this identity, and maybe the chain is not homogeneous. So maybe the chain at time 1, you jump from x to y with a probability which depends from time 1. Time 2 depends on time. So here I started by considering Markov chains in which the probability that you jump from a point to another point does not depend on the time, while you could define a Markov chain in which these probabilities depend on time. Okay? So if this probability do not depend on time, what we have, it's exactly what I stated before. Okay, but maybe they do depend, so what we can prove is this. So let's say that this would be a more general definition of Markov chains, but since I will be working here with homogeneous, I define it in that way. So is that clear? So this means that a process is a Markov chain if and only if the past and the future are independent with respect to the present. And a consequence of that is that if you take a Markov chain and now you look it at backward in time, then you get a new Markov chain. So So a corollary of what we just proved is that if xn it's a Markov chain. And now if I fix a time t, and I defined yk to be xt minus k, so I'm starting at time t, and I'm looking at this chain backward in time. So this is a new Markov chain. Right? Just because since xn is a Markov chain, this means that past and future are independent with respect to the present. And, well, if I look it backward, what's past becomes future, and what's future becomes past. We have, therefore, that for the process y, past and future are conditionally independent. And this means, therefore, from this result that y, it's a Markov chain. Okay, but now y, the transition rates of y will depend on time. Okay? What we proved is that y will satisfy this identity, but now if you compute the jump probabilities, they will depend on the time. So an exercise will be consider a Markov chain and compute the transition probability for the backward Markov chain. So questions?
Even if X is homogeneous on time?
Yeah, even if it's homogeneous on time, so that the backward will depend on time. Further questions? Fine. So now, I want to change topics, and what I want to investigate is convergence to equilibrium. So let's consider our Markov chain. And remember that I have mu, which is a probability measure, which is the initial distribution of my chain. Now, let me define by mu k the distribution at time k of this chain. So mu k of x will be equal to the probability that xk is equal to x. So mu k, it's a new probability measure defined on E. And, well, we can express these probability measures in terms of the matrix P and the measure mu. So this is equal to the sum over y0 up to yk minus 1 of the probability that x0 is equal to x0, y0 up to xk minus 1. And we have seen that this sum, this probability, it's mu of y0 p y0, y1 up to p yk minus 1 x, and that this it's equal. So what it's appearing here is that when you're summing over yk minus 1, what you're doing is you're multiplying these two matrices and computing the product at the point yk minus 2x, and you do that, you proceed backwards by induction. So what you get is that this is mu pk at x. Okay? You agree? So we have, so what mu k, it's actually you take mu, you take p to the power k, and you multiply this line vector with the matrix. Now, I would like to investigate this distribution as k tends to infinity. Say that you start from a point. At time 1, well, you jumped somewhere, so you have a distribution. Then at time 2, you jumped to a new point, so you get, is this converging or not? And what are, there is a sound, tem barulho aí. Conseguem desligar esse barulho? De vez em quando toca, parece celular recebendo uma mensagem. So another thing, so the person who asked me to speak in English is not here anymore. So maybe we can turn to Portuguese. So people watching the video, if you want me to continue in English, please send a message to Google Classroom. Okay? And if nobody send anything up to next class, then I will proceed in Portuguese. Okay? So I want to investigate these limits of mu k. The first observation is the following. If mu k converge to some pi, and what do I mean that mu k converge? Well, mu k, it's a vector. So by saying that mu k converge to pi, what I mean is that mu kx converge to pi x for all x in E. Okay, so suppose that mu k converge to pi. What I claim is then that pi multiplied by p, it's equal to pi. Right? And well, and this is more or less clear. Suppose that mu k converge to pi. Mu k, it's equal by this representation to mu pk. But I can write this as mu p k minus 1 p. All right? This is clear. Now, mu pk minus 1 as k converges to infinity, it's converging. Well, this is mu k minus 1 p. Mu k, it's converging to pi. So this is converging to pi p, while this one, it's converging to pi. Okay? So you got that, you got this relation that pi, it's equal to pi p. So this is what I will call a stationary probability measure. So I'll say that pi, it's a stationary probability measure if pi p, it's equal to pi. Questions? Mais alto que o nosso. Okay, there is an, okay. So we continue in English. So this is the definition of the stationary, and why is it, well, and in particular, if pi is stationary, then let me define if nu it's a probability measure. So remember, I define px, which is the probability p condition that at time 0 I'm at x. So now if I have a probability measure nu, I will define p of nu as the measure in which you start from the distribution nu. So this is a new measure which is equal to the sum in E of nu of x, p of x. And so that pi nu that x0 it's equal to x, it's equal by the definition the sum for x in E of nu x. Okay, let me call that y. Pi x, px, x0 it's equal to y. But under this measure, px, the initial state, it's x. So this is 0 for all y, but and equal to 1 for y equal to x. Okay, so this is delta xy, which is either 1 if x is equal to y, or 0 if x is different from y. And when you sum that over all x, what you get is that this is nu y. Okay, so this is a new probability measure, which starts from the distribution nu at time 0. Now, what I claim is that if pi is stationary, then p pi, well, we know already that at time 0, the distribution is pi, but what we have is that at time k, it's also pi of x. Right? Because we have seen that this distribution here, it's pi pk. And since pi is stationary, pi p is equal to pi, which means that pi pk is equal to pi. And this is why it's called stationary. Right? If you start at time 0 from this distribution pi, you let the process evolve, and what you observed at any time, it's this distribution pi. Okay, questions? So what I want to investigate, it's, well, is there always a stationary distribution pi? And is it true that starting from any distribution, you converge to pi? So existence, uniqueness, and convergence. Okay, so any guess about uniqueness and existence? Okay, let me prove that there is always one. So there is always one. And here's a proof. So I fix a point x, and I started from this point. Okay, so I'll consider pi x. And so this means that pi x distribution at time k, this is just the measure concentrate on x pk y, and this is pkxy. Okay, so delta x, it's the measure which it's concentrated on x. Okay. So let me prove that there always exists one. So what I will do is let me define the sequence mu n as 1 over n, the sum of k equal to 0 up to n minus 1 of these measures. Or, if you wish, of any, I can start from any distribution mu, but I could start from 1 point. It's not important. Okay? So now I have defined the sequence of probability measures, and what I will do is I will use compactness to extract a convergent subsequence. Okay? So I assumed E to be finite, so E can be represented by x1 up to xm. These are all the points. So now I consider the sequence mu n of x1. So mu n, it's a probability measure. So this sequence, it's positive and bounded by 1. So I can find a subsequence, which I will represent by n1, for which mu n x1 converge to a limit, which I will represent by pi x1. Okay. Now, once I get this subsequence, I extract a further subsequence for which at x2 you also converge. And I go further, so at the end, since this set is finite, what I get is that I can find a subsequence n prime such that mu n prime of x converge to a limit which I will represent by pi of x. And this is for all x in E. Okay? So this is just using the compactness of the interval 0, 1. One observation is that pi of x, it's of course non-negative, and also that the sum of pi of x, it's equal to 1. Because pi of x, it's equal to the sum for x in E of the limit mu n prime of x. But this sum, it's finite, so I can change the limit with the sum. Now, mu n prime, it's a probability measure. So the sum over x of mu n prime, it's 1. So this is a constant sequence equal to 1. And therefore, the limit, it's 1. So pi, it's a probability measure. And now I claim that pi p, it's equal to pi. So let's prove that pi is stationary.
But if you prove that the subsequence converges in pi, it would also be already be stationary, because you just prove that there is convergence, then the limit is stationary.
Yeah, but I don't have that. It does not converge. It's a subsequence which converge.
But you can take the subsequence, and as the subsequence converges, the limit has to be stationary.
No, because in my argument, it was important. Did I erase it? Yeah.
Okay, depends on the axis.
No, it's not that. In my argument, this sequence, I took this sequence. And I could prove this sequence because I could represent mu n as mu n minus 1p. But this is not true anymore. So this identity was fundamental in order to prove that the limit was stationary. And now I don't have this anymore. So I need an argument, but the argument is very similar. The argument is very similar because I have, by definition, that mu n p, it's equal to, I'm applying p on the left, on the right, so I'm applying p on the right, and what I get is that this is equal to 1 over n, the sum k from 0 to n minus 1, mu pk p. Okay? So this is pk plus 1. And I can rewrite this as 1 over n, the sum from 1 to n of mu pk. And this is equal to, now, so I want to represent this in this form. So I will rewrite this as the sum from 0 to n minus 1 mu pk. But of course, here I have added the term 0, so I have to subtract. And I have here the term n, which does not appear here, so I have plus mu pn. All right? But now, this first term, it's what I call mu n. So if I take now the subsequence, prime, now I know that the subsequence is converging. So this one is converging to pi p, because the subsequence is converging. And this term here, it's mu n prime. So it's converging to pi. And these ones are converging to 0 because they are divided by n. So I get that pi p is indeed equal to pi. So they always exist as stationary state. Okay? If the set is finite. So questions? Okay, so existence, it's easy. Now let's look at uniqueness. So give me an example where you have more than one stationary measure. Como? Dois estados. O segundo não pode passar para o terceiro, o segundo passa para o primeiro.
Duas cadeias de Markov separadas, cada uma tem
totally. Okay, so the simplest one, it's this one, which is, okay, you have two states. You jump from one to one, the other to the other, and so you have two stationary states. One which is concentrated on here, and one which is concentrated here. Okay? And this is the typical example. It's that you can decompose your space in sets for which you cannot go from one set to the other and from the other to the one. Okay? So to avoid these type of examples, I will introduce a condition which is called irreducibility. So I'll say that a chain, so a matrix P, it's irreducible if you can go from any point to any point. So this means that for all x, y in E square, there exists n such that Pn xy, it's really positive. Okay? From you choose any 2 points, you can go from one point to the other. And I will impose this condition to avoid these examples. Okay? If this condition is not satisfied, you just look at a subset at which it's satisfied, and then you study your Markov chain on this set. So typically, you'll have one state. It will jump to one state. This state okay, so that chain would not be irreducible because from this point you cannot go to this point. Okay. But you have what's called irreducible classes, but I will not study this. So you take the sets which are irreducible. So these two sets are irreducible. And now you study the Markov chain in this set. Since they are irreducible, and it's the smallest one, this means that you can visit all states from one state you can visit all the other states inside this class, and you don't leave the class. So if you restrict your chain to this set, you have a new Markov chain. Okay? So that's what you do, but I don't want to enter into these problems. I'll just assume that my chain is irreducible. Okay? And now, I claim that if the chain is irreducible, then there exists a unique stationary state. Okay? So this is maybe a theorem. So I always, from now on, I will always assume that my chain is irreducible. So state space is finite, my chain is irreducible. And here, how I prove this, let me take phi, a strictly concave function. I know that there exists one stationary state. So let me call pi this a stationary state. My first observation is that pi of x, it's strictly positive. So let me write it here. My first observation is that pi of x, it's strictly positive. So for all x, pi of x is strictly positive. Why is that so? Well, I know that pi, it's stationary, and I know that the process is irreducible, so I can go from any point to any point. So since pi is a probability measure, there exists at least one point at which pi is really positive. Okay? Since the sum of pi of y is equal to 1, then there exists x0 such that pi of x0 it's strictly positive. Okay. Now, I know that I can, so I fix y, and I want to show that pi of y is strictly positive. So for that y, I know that there exists n, such that Pn xy, it's strictly positive because my chain is irreducible. Well, I know that pi, it's equal to pi p, and by iterating this relation, I know that pi, it's equal to pi p to the power n. So now, this tells me that pi of y, it's equal to pi pn of y. Okay? But pi pn of y, it's the sum in x of pi x, pi n xy. And this is larger or equal than pi x0, pi n x0y. Pi x0, it's really positive. Pi n x0y, it's really positive, and therefore the product is positive. Okay. So if you have
Carl is asking if taking the irreducible chain separately, can we talk about the depth of the other chain?
the death. Well, I don't know how to put it. You just, if you have these irreducible chains, so you want to investigate your Markov chain. One way to do that, it's you investigate what happens in one class, irreducible class, in the other irreducible class, and this tells you how the Markov chain behaves. So it's not saying that it's just that while you're considering a sub-Markov chain, a Markov chain inside a subset, and because what we can prove is that if you have a Markov chain, you can decompose your Markov chain in irreducible sets, and all points which are not, all sites which are not in the irreducible sets, they will end up in one of these irreducible sets. So this is exactly my example. In my example, I had one point which was jumping with probability p and say 1 minus p to these two irreducible sets, which means that, well, in finite time, you will hit one of these irreducible sets, and once you hit, you remain there for the rest of your time. So what you, so these points, we will call them transient points, so that you visit them only a finite number of times, at the end of which you will hit one irreducible set, and you will never return back to these sets. So there are these transient points which you don't care too much because you visit them only a finite number of times. And then what's important is to study what happens in these irreducible classes. but I don't want to enter into this discussion because that will take me some time, and all my examples will be irreducible. Okay, so let's concentrate it on irreducible. And as I said, my first observation is that if the set, the Markov chain is irreducible, then any stationary state, it's really positive. Okay. Fine. Now, I want to prove that it's unique. So I will assume that there is another one, mu. And I will define, so let me call mu n. Actually, let me take mu any probability measure. So I won't assume that mu it's stationary. Let's take any probability measure because the inequality I will prove it's interesting by itself and doesn't require mu to be stationary. So let me take mu any probability measure, and let me define mu n as mu pi n. So this sequence. So it's the distribution at time n starting from mu. And then I define a functional h, which is defined on the probability measures. And this functional, it's equal to the sum over all points of pi of x, phi. So phi, it's my strictly concave function, of mu x divided by pi of x. I can divide by pi of x because pi is stationary, and I just proved that pi is really positive. Okay? And what I claim is that h decrease. So h of mu n it's larger or equal than h of mu n minus 1. Or if you wish, that h of mu p, it's larger or equal than h of mu, and it's equal, so it's strictly less, greater, and it's equal if and only if mu equal to pi. So let's prove this inequality. So by definition, this is the sum for x in E of pi x, phi of 1 over pi x, mu pi of x. And this is equal to the sum x in E, pi x, phi. So what's mu pi? It's the sum over y of mu y pi yx. So now I want to divide that by pi of y and multiply this by pi of y. And replace this pi of x by pi of x. Okay? Now, this is alpha of y, and what I claim is that the sum, it's 1. So the sum in y of py x divided by pi of x, well, you see that this is 1 over pi x, pi p of x, but since pi is stationary, this is 1. Okay? So what I'm doing here, I'm taking a convex combination of these weights. And since phi is concave, this value, it's strictly, or it's large or equal, and if these quantities are not all equal, it will be strictly larger, then the sum for x in E, pi of x, then you get the weights, which are pi y yx divided by pi of x of phi mu y py. Okay? And, well, and I forgot to sum over y. All right? So this is just using the fact that phi is strictly concave. So remember that this is strictly larger if these weights are not all, if these values are not all constant. Fine. But now pi of x cancel with this pi of x. And if I sum over x, P it's a transition matrix, so the sum is 1. So this is equal to the sum over y of pi y phi of mu y divided by pi y. Okay? And which shows that indeed this inequality holds, which means that if you start, so that's a very nice result, because you just defined a functional which is decreasing along time. And it's strictly decreasing unless mu divided by pi is constant. But if mu divided by pi is equal to a constant, since mu and pi are probability measures, then they have to be equal. And this proves uniqueness. Okay? Because if mu is stationary, mu pi is equal to mu, so we have identity here. And since we have identity, so the ratio has to be constant, and therefore mu has to be equal to pi. So a consequence of this result is that you have uniqueness of stationary measures, but it's much stronger. Because you see here, phi, it's any concave function, and you proved that you have a functional, or a family of functionals, which are decreasing a long time. So questions?
Did you use the hypothesis of reducibility in the convex coefficient?
No. No, just use just irreducibility in order to guarantee that pi is really positive. Because that's the problem. When you have, if it's not irreducible, what this tells you is that these pi's have disjoint support. Okay? So if you take pi again, and if you take a measure which is absolutely continuous with respect to pi, and is stationary, then mu is equal to pi. But, so I needed irreducibility just to guarantee that pi is strictly positive everywhere. Okay? So in the other examples, you could have a pi here, another pi there, but there is a unique pi in each irreducible class. Questions? Okay, so we know that if it's reducible, then we have a unique stationary state. Now the question is, are you converging to this unique stationary state? So you start from a point. At certain time, you have a distribution. Is this distribution converging to the stationary state? And the answer is no, because what can happen is, here's the simple example. You have 2 points. You jump from one to the other. Okay, so the stationary state pi, it's equal to 1/2 of d0 plus 1/2 of d1. So you put weight 1/2 and 1/2. But clearly, you don't converge, because if you start from 0, at even times you're at 0, and at odd times you're at 1. So that will never converge to pi. Okay, so p n xy will never converge to pi of y in this example. And this is because, well, the chain, it's what we call periodic. Because if you start from 0, you visit 0 only at even times. So there is a periodicity. So I introduced here one condition. Now I will introduce a second condition. And this second condition are sufficient in order to guarantee convergence. And this second condition, it's called aperiodicity. So remember, E, it's finite, and the chain xk, it's irreducible. Now, I want to define periodicity. So let me take a point x, and I will look at all n larger or equal to 1, such that Pn x, it's strictly positive. So this defines a set A of x. Okay. And I will take the greatest common divisor. How do you call that in English? Greatest common divisor? Yeah, is that? Greatest common divisor, okay. Of this set A of x. Okay? And I will say that the chain is aperiodic if the greatest common divisor is 1 for all x in E. Okay? So this is definition, and therefore, in this example, this is not satisfied. So an exercise for you to prove is that this greatest common divisor does not depend on x. So under my assumption that the set is finite and irreducible, then the greatest common divisor of ax, it's equal to the greatest common divisor of ay. Okay, and so I'll give you a hint about so you have your point x and you have your point y. So you have, okay. So this greatest common divisor of ax tells you when you can return to x. Now the chain is irreducible. So you know that you can jump from x to y in n times and from y to x in m times. So what you do well, what you conclude from that is that you can return from y to y after m, well, the number of jumps here plus n. Okay? And you'll use that in order to prove this identity. So this is one observation. The second observation, and mind that here I'm using the Markov property, right? Because while I'm going from y to x, then I'm stopping at x, and I'm starting the process at x, and I'm visiting x. So you'll need the Markov property. And then a second observation is the following. So AX, it's has a very simple structure in the sense that if M and N belongs to AX, then the sum belongs to AX. So if you can return from x to x in m steps, and in n steps, you can, of course, return in m plus n steps. Okay. So from that, it follows that assume that AX, say that the greatest common divisor of AX is equal to 1. What I claim is that this implies that there exists n0 such that pi n xx, it's strictly positive for all n larger than n0. And let me try to convince you of this fact by an example. An example is that, okay, so let's assume that P4 xx is positive and P9 xx is positive, just to give you the argument. So this tells you that you can return to x after 4 steps and after 9 steps. Okay, so what I will do, I will consider the group 0, 8 or 1, 9, and I will start adding 4 in this group. Okay? So since I can jump from x to x in 4, I can return in 4 times. I can also return 8 times. And this means that I can also return in 4 plus 9 or 8 plus 9. So okay. Now when I sum 4 again, I'm out of 9, but I'm reduced 12 minus 9, it's 3. So which means that I'm here at 12. But 12 corresponds to 3 in this, if you wish. Which means that in these second interval of 9, I have the place 4, which is occupied, 8, which is occupied, and now also the 3. Is it clear what I mean, or? More or less, okay. So let me repeat. What I'm saying is that I know that I can return in 4 and a 9. So here are 4 and 9. So now by using this property, where is that? This property, which means that also 8, I can return 8. Okay? And now I will sum 4, but when I sum 4, I'm out of this set 1, 9, so I'm considering now the interval 9 up to 18. I know that I can jump in 4, I can jump in 8, but now if I add 9 to these two numbers, this means that I can jump in 13 and in 17. Okay? But I can also jump in from 8 plus 4, 12. But I want to write these 12 in this first set. And let me put it 2, just to mention maybe that I'm in the second interval. So I can jump in 12 and also in 16. But if I go back by 9, this 16 is represented by 7. Now I go to the third interval, because at 16, if I add 4, I'm at 20. Okay? But now I can add 9 to all these intervals, to all these points, and get that 12 plus 9, it's 21. 13 plus 9, it's 22. 16 plus 9, it's 25. And 17 plus 9, it's 26. So I can jump from x to x in 21, 22, 25, and 26 steps, but also in 20 steps. Okay? And this 20 corresponds, by taking out 18, to the number 2. So here was 3, and here was 7. But here I can also jump from x to x in 20 steps, but this 20 minus 18, it's 2. So let me write 2 here, and this is in the third interval. And now I can jump also in 24, but 24 minus 18, it's 6. This means that I'm almost filling the interval 1 to 9, because I already filled 2, 3, 4, 6, 7, 8, which means that in this third interval, I'm covering all these points. All these points translated by 18 are covered. But there are still some points which are missing. So 18 plus 9 is 27. And I'm here at 20, so 24, and 20, now 28. So 28, it's already on the fourth interval, and it corresponds to the first. 28 minus 27, it's 1. And this corresponds to the fourth interval. And now 28 plus 4, it's 32. 32 minus 27 is 5. And this corresponds to the fourth interval. And now 32 plus 4, it's 36. But 36, it's exactly corresponds to 9. And so this is in the fifth interval. So in this way, I covered all these points from 1 to 9 in this last interval, which means that in this last interval, all these points are covered, which means that Pnxx, it's positive for all these points. Therefore, I proved that Pnxx, it's strictly positive starting from 27, if I didn't make any mistake in these computations.
Isn't this equivalent to that number theory theorem in that sense that when you have a list of positive integers graded from divisor equals 1, that there is a minimal element?
No, this is exactly what...
I think the product of the elements of AX is the lower bound. But it's equivalent, right?
It's exactly this theorem. Okay? So this is telling you, let's say that the, okay, so, okay. Louder.
The way I think is, so basically what you are saying is that you can generate any natural number starting from 1 and 0, that it is a multiple of 4 plus
I didn't understand. Okay, we can discuss that at the end. Okay, well, just to convince you that this theorem is correct. Okay? Well, and if the greatest common divisor is not 1, it's a k, then that you just multiply this n by k. Okay? But once you prove that, then it's easy to prove this one. Because if the greatest common divisor here it's 1, this means that there exists an n starting from which you can always return, which means that starting from y, you can return to y after m plus n plus these points. And this tells you that the greatest common divisor of y has to be 1. Okay? So this result with this observation comes from this result. Okay? And some Markov argument. Fine. So the theorem which will use these results is the following. So assume that E is finite, that the chain is irreducible, and aperiodic. Then for all x, P n x y converge to P of y. So for all x y, where pi is the unique stationary measure. Okay? So this is what we are going to prove. And the proof relies on a coupling argument. Okay, maybe it's I stop here and I present that Tuesday. Okay? So, diga. Pode.